Hi everyone, let's talk about energy transfer and specifically heat transfer. There are three ways to transfer heat. The first way is through conduction. Now conduction is when you put your hand on a hot stove and heat moves right from the hot stove into your hand. So direct contact with matter. And you need to be aware of two situations. You have your good conductors and your poor conductors. So when you're cooking, you should use plastic or wooden spoons because those are poor conductors of heat. And you should avoid using metal spoons because as you stir your stew or whatever you got cooking on the stove with a metal spoon, eventually the metal spoon will get hot and it can transfer heat to you and you could get burned or at least be uncomfortable. Second way to transfer heat energy is through convection. Convection is where warm air rises. So heat is being transferred from something hot into the atmosphere and ultimately onto something else. And finally, the third way is through radiation. The hot object actually gives off light. And we talk about something being white or red hot. White hot, red hot is that they're glowing because they're so hot. And when objects are very hot, they can emit light that we can see. But it turns out that all objects emit some light. So here's a little diagram showing a campfire and the three ways of energy being transferred from the fire to us. The first way was by conduction. So this guy's got this poker here and it's glowing red hot down here because it's getting really hot. And that heat is traveling up the metal rod and he's got a glove there so it didn't get burned. Conduction, direct contact with hot objects, transfers that heat. Second way is over here by convection. The hot air rising off of the fire is warming up this person's hands. So the flow of the air, in this case the fluid, is drying up the heat and transferring up to the hands. And then finally we got radiation. So if you're ever at a campfire and you put your hands out from the side and you feel some warmth, well, those aren't hot gases coming out sideways. The hot air is going up. So instead, what you're feeling from the side is radiant light, infrared light actually, and some visible light. And that's that light energy that's striking your hands, and your hands are absorbing light energy and feeling some warmth, getting warmed up. And so heat energy is transferring from the fire to your hands. Okay, now here's a thermos bottle, and in the thermos bottle we're trying to minimize heat loss. So we got to take care of all three forms. So here's a cutout of a thermos bottle, and you can see that it actually has two walls. And there's a space in between the walls. Down here we got a little side view cutout and a vacuum in between those two walls. And what that's doing is trying to prevent both conduction and convection. So conduction is where the hot fluid, let's say there's soup in here, hot fluid is heating up the inner wall. But with the vacuum here, the outer wall is not in contact and is not being directly heated up by that hot liquid. And so the outer wall, the outer part of the container, could be cool or it could be hot or whatever. There's no heat transfer, ideally no heat transfer by conduction from inside to outside. And since this is a vacuum here, we're not allowing any fluids, any air to touch this hot liquid and come out. The plug really is preventing convection. Convection would be where cool air could go inside, get warmed up by the hot soup, and then the warm air could come out, allowing more cold air to draw back in and draw out more hot air, and the heat would then be transferred out. And finally, these thermoses are silver, the reflective, so that as a hot soup radiates light in the infrared, it actually reflects off the inside of the container and right back into the soup to keep it warm. Oh, and so we usually, well, at least I do, I think about a thermos trying to keep my hot cocoa hot. But you can put cold drinks in there on a hot summer day and they'll stay cold too. And the idea is that you're preventing heat transfer of the hot afternoon sun from that heat going into your cold beverage, right? Block the conduction, don't allow the hot outside air to contact the cold beverage inside. Keep the plug closed so that the hot air doesn't go in to get cooled off by the cool liquid and come out as cold air, drawing in more hot air. And then finally, radiant light from the sun isn't shining on your cold beverage and warming it up. So here's a cheap thermos bottle, not even a thermos, right? This is just a coffee cup, but it's designed to minimize those three ways of transferring heat, right? You got this cover here to form some insulation. It's a poor conductor. And so as you hold on to this cup, it's putting a gap here in between the liner and the cup to prevent conduction, your direct contact with the hot coffee or the hot container. Minimize heat transfer that way. It's got a lid here to prevent convection as hot air rises and cool air comes in to draw off that heat. And then, well, I suppose it's white. Maybe it's because it's reflective. Doesn't emit much light, doesn't absorb much light. Actually, it's hard to tell because we see in the visible light spectrum. And unless this coffee is glowing red hot, we're not going to be able to see the light that's coming out. Okay, a little bit more about convection. Heat transfer through the motion of fluid, whether it's air or water. And most of the time we think about it as air. So when I say that hot air rises, what's that really happening there? Well, the energy that's going into the air, it's being heated, causes the air to expand. And then as that air expands, well, it becomes less dense, right? If you think about, the certain amount of air having some mass, some weight, well, as that amount of air expands, it's not going to lose any mass. It's just going to fill up more space. It's going to occupy more volume. And remember that density is equal to mass divided by volume. So density is directly proportional to mass, more density, but it's inversely proportional to volume. More volume means it's less dense. Okay, so as the air expands, it becomes less dense. What does that mean? Well, that means it's going to rise because of the buoyant force. Remember, the buoyant force says that objects will float when they're less dense than the surrounding fluid. So if you got some air and there's cold air around it and this little packet of air gets hot, it expands and becomes less dense than the air around it. So hot air rises. As the air expands, it cools down. And we can talk more about the mechanism of this in class, but it's just true that the expansion of air causes a cooling effect. If you think about how you blow on some hot soup, you kind of purse your lips. But if you want to clean some object that's made of glass and you want some water vapor on it, some steam, you don't purse your lips as you blow. Why is that? Well, if you open your mouth wide, you let out all the hot air out of your lungs, and it carries a lot of the hot moisture in it, and a lot of moisture transfers out. But when you purse your lips, you actually pressurize the air inside your mouth, and as it's let out through your lips, it's expanding. That air expands, and the hot air that was inside your mouth, as it expands outside your lips, it cools off. Try it. Let's talk a little bit more about light, also known as electromagnetic waves. And just like waves at the ocean or on a lake or in your bathtub, waves are described by wavelength, meaning you got this wave and, well, how far apart are the tops, the crests of the peaks? You can measure that distance, and that's your wavelength. You can also describe waves as to how fast they vibrate. That's a fast vibration, a fast frequency, and this is a slower frequency. How many times they vibrate per second. And just the action of making high frequency waves takes a lot of energy. Well, that's true for light too. The higher that light vibrates, or higher its frequency, the higher the energy. And just by definition, if it's vibrating very quickly, it's going to mean that the tops of those crests are really close together. They're really short. So you get short wavelengths. Okay, then finally, when we talk about light in an everyday manner, we think about light that we can see. But light exists as both visible and invisible light, and our eyes are only sensitive to a very narrow part of light, a very narrow range of frequencies. So let's take a look at the full electromagnetic spectrum. When we think about light, most of the time we think about visible light. And right here, this little narrow range, around 10 to the 15 cycles or vibrations per second is the frequencies of light that our eyes are sensitive to, that we can actually see. Now, if the wavelengths of light vibrate even faster, they'll have higher energy, and we call that UV, or ultraviolet light. Faster than that, well, then you get X-rays. And you've heard about the dangers of X-rays. If you go to the dentist, you need to wear those lead vests that try and protect your bodies from X-rays. And then beyond that are gamma rays. If we go the other direction, go to weaker, less energetic light, well, we have infrared light, IR light. That's just below the range of the red. Oh, why is that? Well, as you look at visible light, the shorter wavelengths, 400 is shorter than 700. That means 400 is faster moving, higher frequency. That carries more energy. So the blue light is more energetic than the red. And so if we talk about going to wavelengths of light that are even longer or even less energetic, then we're talking about below the red. And so that's infrared. If you slow down the vibration of light even further, you get the microwave energies of light. And even slower than that, then you get the radio waves. Okay, so it turns out that all objects emit radiant energy, emit light, and if it's hot enough, like this flame, then we can see that light coming out. And actually, as you look at the colors of these flames, you can probably guess which one's the hottest. Yeah, the blue. The more blue it is, the higher frequencies, the more blue, the hotter the flame. And the yellows and the reds and oranges in there are lower wavelengths. Sorry, lower frequencies of light and less energetic. Still pretty hot though. And so it is true that the frequency, the highest, the most common frequency of light that comes out of an object, the peak frequency, that's proportional to its temperature. Hotter the object, the more blue or higher energy light that comes out. Here we got some infrared images. So there's a special IR or infrared camera that was used at a zoo at the same time of day. And here you can see the giraffes are in the warmer wavelengths than the cold-blooded turtles. Okay, so all objects give off energy, and it also turns out they can also absorb it. And then the idea is that if you have an object at a constant temperature, what that implies is that it's absorbing the same amount of energy and light that it emits. Okay, let's talk about the greenhouse effect and global warming. Sunlight, typically high energy, high frequency light, is going to pass through the atmosphere or through this glass material because it's transparent, which means it's not going to be easily absorbed. And then once it gets inside, well, those other objects, like the Earth's surface, or the plants inside, or the tables, whatever's inside the greenhouse, they can absorb that high energy light. And as they absorb that energy, they warm up. Energy increases their temperature. And as they warm up, they can emit more light. And typically it's a low frequency light, right? They're not glowing red hot or white hot. So it's going to be that infrared light that we talked about. Okay, that low energy light, the low frequency light, turns out that's opaque to glass. Glass absorbs infrared light. So that's weird. If you could see an infrared, well, then glass would appear black. It would be absorbing the infrared light. And you can't see through glass if you're looking at the infrared. The infrared light actually gets absorbed by glass. Well, glass is transparent to us because glass does not absorb visible light. And so the visible light passes through the glass, and we can see objects on the other side of glass because the light from those objects passes right on through the glass. Okay, well, if you've got back in this greenhouse that those objects are glowing in the infrared and the glass itself can absorb the infrared light, well, the glass will then warm up and start emitting in the infrared light also. And sure, some of that infrared light can come outside the greenhouse, but most of it goes back in. And so it turns out that inside the greenhouse, you have more absorption than you do emission of light outside the greenhouse. And since the absorption rates are higher than the emission rates, the temperature is going to rise. And that's what we think is happening with global warming. There is a greenhouse effect that's been measured. Sunlight comes in, largely visible light and ultraviolet light, and it turns out those wavelengths of light are invisible to most of the gases of our atmosphere. The visible light and the ultraviolet light get absorbed by the planet's surface and by the water, which then warms up and emits infrared light. Well, it turns out that water vapor and carbon dioxide, stuff emitted by us, people and animals, that forms some of the gases in our atmosphere, they absorb in the infrared. So this infrared light coming off of the planet gets reabsorbed by the gases that make up the atmosphere. And then they start glowing and shine the infrared light in all directions, some of which escapes, but a lot of it gets reflected back to the Earth, where then it's reabsorbed and warmed up, and then the surface warms up again. So the greenhouse effect is real. The controversy is, how much is the planet's surface warming up over time? What is the global warming effect? And so that's something we can talk about in class. Finally, you're more familiar with the greenhouse effect happening in your car on a hot summer day, right? So the sunlight comes into your car, and without this visor, it heats up the interior of the car, your car seats, and then they get really hot, and they start glowing in the infrared. Well, the infrared light gets absorbed by the glass, the windows, and the glass will get hot. You can feel that on a hot day, and they start glowing in infrared, and some light goes right back into the car and reheats it up. So it locks it in there, and the interior of the car gets really hot. So you can buy these visors, and the idea is as the visible light comes in, it reflects off the visor and comes right back out of the glass. While it's still in the visible spectrum, it's still high energy, high frequency light, so it can pass right back out through the windshield. And it doesn't get a chance to be absorbed by the dashboard or the seats. Okay, that's all for now. Thanks.